Okay. So, now let us see what do we do about this. Okay. So, this kind of integral which I showed you is what is called a improper integral. Okay. So, this is the best example. I have an integration from minus a to b, some function which is blowing up, and since there is a point in between which blows up at infinity, this is called an improper integral. Okay. This is just the definition. Right. So, how do we, I mean, what I showed you previously, both were sort of improper integrals, because both log x and 1 by x, they were blowing up. Okay. Do not worry so much about the limits over here. Previously I was going from epsilon to a, but I may as well have gone, I could have written the previous example as something like this, log of mod x, and gone from minus a to b. The same thing would happen, right? I would break it up into two parts and right. So, in order for you to answer whether or not this integral is convergent or divergent, this is again a bit of revision from calculus. What you should do is you should break this up as minus a to eta 1 by x dx plus epsilon to b 1 by x dx. Okay. And is there a term that I am missing over here? So, no, that is fine. Yeah. So, I break this up in this fashion, and if it happens that as eta and epsilon both approach 0 independently and the limit exists, then we say that the integral is convergent. So, to understand this a little bit more sort of carefully, what we can do is we will take a counter, I mean let us do something else. Let us do minus a to minus epsilon dx by x plus, let us make eta and epsilon to be the same. What can I write for this? What will the first term give me? I can do a substitution, x is equal to minus y, right. So, there is no problem in taking log, I mean it will not become log of a negative number. So, what will happen? Dx will become minus dy, right. I can do all of this. What will I get over here? Log of, what do I get? Okay. Simple integration, just do a change of variables, x is minus y, that is what you get. First term. Second term, log of b minus log of epsilon. So, what is that equal to? Log of b by a. So, it seems that this integral exists, but what happened? First thing I did is I made eta equal to epsilon. If I make eta equal to epsilon, both are going to 0 at the same rate, because they are identical variables, right. Now, supposing I did I played a little bit of a trick. I said that let me do the following. Okay, let me instead do this as minus a to minus 2 epsilon, let us make this 2 epsilon dx by x plus epsilon to b dx by x. So, what have I done? I have gone back to eta, I am calling as 2 epsilon. Now, eta is approaching 0 faster or slower as epsilon tends to 0. Eta is 2 epsilon, eta is approaching faster because 2 times epsilon. So, epsilon is going to 0 at some rate and 2 eta is going at twice the rate. Okay. Now, when I evaluate this integral, what do I get? So, I am going to get log of 2 epsilon minus log of a plus log of b minus log of epsilon. So, what happened over here? I got log of b by a plus log of 2. So, what happened? So, now you see appreciate the meaning of this definition. If both of them independently approach 0 and the limit exists, then the integral is convergent. So, we saw that if these two are approaching at different rates, then you got this funny log 2 appeared over here. Similarly, any term, if I made it 3 epsilon, I will get a log 3 over there. So, this limit itself is not existing as both eta and epsilon are approaching independently. Okay. So, this is the definition of a divergent integral. Okay. You can try it out for the other case log of x, you will find out that it is convergent and there is no problem therefore. Okay. But 1 by x has this problem, therefore, it is a divergent integral. But what existed was this term existed, right, when they approach not independently, but in the same rate. When they approach at the same rate, it existed, right. So, when they approach at the same rate and I get, I mean the limit exists, it does not blow up, right. So, when it is like this minus a to minus epsilon plus epsilon to b, if it is of this form and this exists, this is called the Cauchy principal value of the integral. Okay. So, the notation for it is PV. So, sort of to summarize, I had a, let us say, a segment over here minus a to b, and there is a singularity sitting over here. Okay. And what is happening as I am going from here, I am hitting the singularity, right. So, what happens is I will write down this integral minus a to b fx dx. I write it as, so I am going to call this the principal value, which is minus a to minus epsilon plus epsilon to b, okay, this integral. And what have I left out? So, minus a to minus epsilon and epsilon to b. I have left out one segment in this, right. So, I have to compensate for this segment somehow, because the integral is from minus a to b. So, the way around it is I have to somehow avoid the singularity by jumping, okay, jumping around it. So, that becomes what is called, I can write that as an integral over some contour that does not go into the singularity. That is how I write this. Okay. So, this is also called the residue. That is the total integral. Okay. Now, again there is a little bit of ambiguity over here. How do I choose this deformation contour? Could I have chosen it like this? Yes, I could have chosen it, right. So, that piece of ambiguity survives, how to evaluate the residue. Okay. The physics of the problem will tell me which contour is allowed, which contour is not allowed. Okay. So, this is something sort of new which you have encountered, is that when you hit a singularity, then you have to do the integral in two parts. The first part is without the singularity, and that is called the principal value, the Cauchy principal value of the integral, right. So, the notation for it is, as I have written over here, you can write down, you can just write down PV of fx dx, right. So, if you see this, it means that the singularity has been punctured out, you are not including it. There is another slightly confusing shorthand notation for it, which goes like this. There is a cut across the integral sign. That cut tells you that the singularity has been escaped. Okay. So, these are the things to keep in mind. So, the principal value is the first part over here, and the second part is going to be the residue term, which we will spend some more time on in trying to evaluate. Okay. So, should we go ahead then and calculate the integral grad 0 at n hat? Okay, let's calculate this integral. Okay. Well, before we get to the integration, we have to see how do we modify our integration contour now, right. So, if you look at this over here, either this or this, any which way I have to escape the singularity, right. So, when I am looking at, let us say, the first equation over here, so I will draw it 2 times. So, this was my first integration, first volume, right. This is my V1 and this is my V2. Okay. For the first equation, r prime is forced to be in V2. Okay. So, let us say that this is my r prime. Okay. I have fixed r prime right now to be this segment, the segment is from here to here. Okay. R prime is fixed, I am trying to write down my one equation. Okay. So, R is going over this whole boundary, that is my contour integration. Now it comes into this segment, so it enters over here, very good. Now it hits the singularity. Which way should I deform the contour? Above or below? It should go below, right? So it should go like this, right? That is why I use the word S minus. So S minus tells me I am inside, right? So this is, you can think of this as closer to the S minus term over here, okay? Similarly, wherever the location is, wherever R prime is, I must bend around it. That is going to be our strategy, right? And for, so this was for equation 1, okay? And for equation 2, I am drawing it separately just so there is no confusion. Again, this is my segment over here, and I am going about my integration. This is my R prime. Now, R prime in the second equation is forced to belong to V1, right. So, what will happen is, that is how I can do this integration, okay. So, that will be the strategy that we will follow, okay. So, we will bring this discussion to a close over here.